Hola a todos, mi nombre es PabloFernandezAlcantarilla y soy investigador en el grupo de Visión por Computador de Toshiba Research en Cambridge, en el Reino Unido. Lo primero de todo quisiera agradecer al Comité Español de Automática Industrial y en particular a los miembros del grupo de Visión por Computador por darme la oportunidad de realizar este seminario. También quisiera dar las gracias a todos vosotros que estáis viendo este vídeo. Espero que el seminario os resulte entretenido y os resulte de mucha utilidad para vuestras investigaciones en el área de visión por computador. El audio del seminario va a ser en inglés para que de este modo pueda tener una mayor difusión. Así que espero que se me entienda bien y espero que me perdonéis mis pequeños problemillas con el inglés. Muchas gracias por vuestra atención y espero que disfrutéis del seminario.
The title of the seminar is Local Features and Applications. Firstly, I will introduce the concept of local features, and also I will briefly mention some applications of interest that are using features. After that, I will review in detail state-of-the-art feature detection and description methods. After that, I will show in detail some applications of interest in computer vision that are based on features. And finally, I will show some conclusions and some future directions about this area of research. Firstly, let's try to answer the following question. What is a local feature? So if we go to Wikipedia, a feature is a piece of information which is relevant for solving a computational task related to certain application. This definition is a bit generic, so I prefer to use the following one in this seminar, which is a feature is a specific 2D structure in the image, such as a blob, corner, or edge, that can be described in a local neighborhood by its appearance information. Normally, when we talk about features, we need to differentiate between detection and description. In detection, we are interested in finding points of interest in the image that are repeatable. For example, we have an image of a particular object of interest. We detect a set of points of interest in that image. Then we have another image of the same object, but the image may be a bit rotated or the viewpoint may be a bit different. So we want to find the points that we have detected in the first image. We want to find the same set of points in the second image. That means that our detector has a high repeatability. And then in description, for each detected feature, we want to compute a distinctive descriptor that can be matched efficiently between different viewpoints and different images of the same object, for example. At the bottom, you can observe two images where a set of features have been detected. These features are depicted by green circles. The size of the feature is represented by the radius of the circle. And you can observe that features normally they are located in areas of the image that they have enough texture information. Features are nowadays very important in computer vision, robotics, and also medical imaging. One of the reasons why they are so important is because thanks to features we can represent an image just by a set of local key points and associated descriptors. So somehow it's a way of compression in which we compress the content of the whole image just by a set of key points and associated descriptors. And there are many applications that are using features such as structure for motion, object recognition, place recognition, and many more. Some of them we're going to see some applications in this seminar. It's been a widely studied problem in computer vision, and now we have many different good methods, and some of them they have great names. You can read some of them in the figure. We have SURF, FAST, DALI, SIFT, FREAK, Lucy, CASE. I will review some of them in this seminar. I will review the most important ones in this seminar, but there are many feature detection and description methods that may be of interest for some particular applications. Now let's start by showing some applications of interest that are using features. The first one is a structure for motion, or SFM, in which we are interested in estimating a point-based 3D model and a set of camera positions of the scene. The scene can be a city, or a monument, or a building from a large collection of photos. So imagine that we have a large collection of photos from the St. Peter's Basilica in the Vatican City, and for each of these photos in our collection we are going to detect a set of features that, for example, in the image the pictures is depicted in pink color. Then we are going to compute descriptors, and we are going to match the descriptors from each of the images in our collection of photos with respect to the other images in our collection of photos, so that we can establish a set of putative correspondences from which we can estimate the 3D geometry of the scene, thanks to the pupillar geometry, and also by solving a large-scale nonlinear optimization problem known as bundle adjustment in the computer vision literature. So now let's watch a video so you can get a better understanding of the kind of 3D reconstruction results that you can expect by using a structure from motion software. So in particular, this dataset is a St. Peter's Basilica dataset, and it comes from Microsoft. In the bottom, you can observe a set of images that they correspond to similar areas in the St. Peter's Basilica. So by detecting features in those images and by matching descriptors across similar images, we can establish a set of putative correspondences, and we can estimate the 3D geometry of the scene. So at the end, we can obtain these very nice 3D reconstructions. Another application of interest is place recognition, in which we want to identify, given a new image, we want to identify if this new image corresponds to a location in our database of images, or on the other hand, this image corresponds to a new location and we need to add this image into the database. So one of the main approaches in the robotics community is FabMap, and FabMap proposes a probabilistic localization and mapping framework in the space of appearance. So FabMap is using only visual appearance information by means of a probabilistic model. What FabMap is going to do is, given a new input image, it's going to detect features, and it's going to use this probabilistic model to estimate a probability if this image corresponds to a new location in our database, or on the other hand, this image corresponds to a previously location in our database and we don't need to add this image in our database. So now let's see a video in which here you have a map. That this map is based on a set of images, and here you can see several images. Some of them corresponds to the query input images, and some of them corresponds to the images in our database. So by means of the probabilistic FabMap is going to estimate a probability if the new input image corresponds to a new location, or on the other hand is a previously visit place in our database. So FabMap is doing all this inference by means of that are represented by these yellow circles in those images. Another example is rigid object recognition. So imagine we have a database of rigid objects, and these objects are they have appearance information by means of features, and we want to perform augmented reality. So the problem here is we are going to have a new image or a new input video, and we want to identify objects from our database in this new input video thanks to features. And once we have the registration between our objects in our database and our input video, we can perform augmented reality. So now let's watch one example from the paper of Pilet and Saito, Virtually Augmented Hundreds of Real Pictures, an approach based on learning, retrieval, and tracking. So in this approach, we have a large collection of postcards in a database. So we are going to have a new input image, a new video. So we are going to detect features in those images, and we are going to find the correspondence between our objects in our database and our objects in our input video. And once we have the registration between our video and our database, we can perform augmented reality in these objects. So for example, we can render logos of universities, or we can render text or any kind of information that we want to show. Now let's talk about similar problem but in this case it's a bit more challenging because we have objects in a database, but these objects are deformable. So the problem is similar in the sense that we have a new input video with several objects that they may suffer from deformations, and we want to find the correspondence between the objects in our image and our objects in our database. And we are going to detect features in our input video, and we are going to match these features with the features that we have in our database of objects. Once we have the registration between our database and our input video, we can also perform augmented reality, but in this case we are also interested in estimating the 3D surface of the deformable object. So at the same time that we have the registration, we can do augmented reality, and also we estimate the 3D surface. So now let's watch an example in which the user is waving the amazing Spider-Man flag. So the system will detect that that object in the image corresponds to the amazing Spider-Man flag in our database of objects. It's going to perform the registration based on features and estimate the 3D surface in this image. So once we have the registration, we can perform cool augmented reality effects such as this one. So we can watch the amazing Spider-Man movie in the flag that the user is waving. Now let's review state-of-the-art methods in feature detection and feature description, and some of the classical methods that are still widely used in the literature. The first one is Harris corner detector. A corner can be defined as a point for which there are two dominant and different edge directions in a local neighborhood of the point. So this detector detects corners, and it provides a measure of corner response. So we have to construct the matrix M, which is basically the sum of first order derivatives in a certain local neighborhood. Normally this neighborhood is 3 by 3 pixels, 5 by 5, 7 by 7. It's a parameter of the algorithm. So we sum the contributions of the horizontal derivatives and the vertical derivatives and compute matrix M. So we have the response of a corner, which is equation number 2, which is equals to the determinant of the matrix M minus an empirical constant, which is K, multiplied by the trace of the matrix M to the power of 2. So this corner response will measure if a given pixel in the image is a corner or not. So as I said before, K is an empirical constant, and normally the values are between 0.04 and 0.056. So you can observe two images at the bottom, which the detected corners by Harris corner detector are depicted in yellow. So Harris, despite that it's a very old method from 1988, is still used nowadays because it has some good performance. It has very good performance. There's a more recent corner detector which is fast, and it's very fast to compute, and it's using segment test. What is a segment test? So fast, the way it classifies if a pixel P is a corner or not is by we have this pixel here at a certain intensity. So in a circle of 16 pixels, for example, we look if there is a set of n pixels in the circle which are all brighter or darker than the intensity plus a threshold t. So if we find these conditions in our local neighborhood, we will classify the point of interest P as a corner. So what's the problem with Harris and fast? The problem is that the size of the neighborhood where we try to evaluate if a candidate pixel is a corner of node is a fixed parameter. And that means that high-risk and fast are not scale invariant detectors. So normally what we want to detect in images, we want to detect features at different resolutions or different sizes. So that's normally the problem. Do we like to detect the tree or the leaves? So if we take a look at this, we have more detail, and we can appreciate better the tree and the leaf. If we go to the other images, the third one, here we have different scales. We don't appreciate so much the shape of the building. So the mathematical to detect features at multiple resolution, it's called multi-scale image processing. And the idea, thanks to multi-scale image processing, is that we can detect and describe features in the image at different resolutions. So these multi-scale methods, most of them are based on the Gaussian scale space for feature detection and description. And the reason why they use the Gaussian scale space is because the Gaussian kernel and the set of partial derivatives of the Gaussian kernel are possible smoothing kernels for scale space analysis. It's important to say that the Gaussian kernel is the simplest option to build a scale space representation of an image, but it's not the only one. And now, how do we build a scale space representation of an image using the Gaussian kernel? So it's very easy. Our original image, L, so we need to convolve this image with the Gaussian kernel to the Gaussian kernel. And the parameter sigma is the scale or the standard deviation of the kernel, so that will measure the resolution or the at which we want to detect features and compute descriptors in our image. So the idea is basically to create a stack of images by convolving our original image with a set of Gaussian kernels of increasing standard deviations. So if we choose a Gaussian kernel with a very large standard deviation, we will obtain an image where details are blurred, and we will have a very coarse image in which we may appreciate the main details or the shape of the tree or the shapes of the building. And if we convolve our image with a Gaussian kernel of a small standard deviation, we will be able to find more detail in our images, and we will detect features at a very small resolution. Another possibility for building a Gaussian scale space is using Gaussian pyramids. So the idea in Gaussian pyramids is to produce a stack of images which are weighted down using a Gaussian kernel and scaled down. So normally the scale space is divided in a series of octaves and a series of sublevels per octave. So when we have convolved our image with a Gaussian kernel with a standard deviation of a factor of 2, we are going to scale down our image, and then we are going to convolve for a new octave with Gaussian kernels until we reach again a factor of 2. So we can obtain this representation as here. So the first row is the first octave. So we have modeling our images, we are convolving Gaussian kernel, and we reach a factor of 2. We now convolve the image with Gaussian kernels until we reach coarse scale representation, in which we don't have so much details, but we roughly have the main shapes of the objects here. Probably the most successful feature detection and description approach that works in a multi-scale framework is the Scale Invariant Feature Transform, or SIFT. SIFT was proposed by David Love, and the idea in SIFT is that the image content is represented by a set of local features that are invariant to translation, rotation, scale, and other imaging parameters. SIFT first detects key points in a Gaussian scale space representation using the difference of Gaussians operator. Computing the difference of Gaussian is very easy. We first need to compute the scale space, the Gaussian scale space representation of an image, and then our difference of Gaussians operator is going to be just simply the difference between two consecutive levels in the Gaussian scalar space. And then per detected key point, SIFT builds a 128-dimensional descriptor that is based on gradients, orientation histograms, and is computed according to a dominant orientation and according to the scale at which the key point of interest was detected. So the idea in SIFT is that, for example, we have to detect a set of key points in each image, and the idea is that common points in both objects, in both images, are going to have similar descriptors, so we can match these descriptors efficiently. Years after SIFT was proposed, a new method came that was the speeded up robust features, or SURF. SURF was inspired by SIFT, but SURF is several times faster than SIFT, and it's a bit more robust against different image transformations. The reason why SURF is faster than SIFT is because it's based on sums of 2D hard wavelet responses that approximate Gaussian derivatives. These hard wavelet responses are computed in a very fast way thanks to the integral images. That it's a special representation of the image that allows for very fast computation or box filters. Having said that, SURF doesn't need to compute the whole Gaussian scalar space representation. Instead, it's going to use hard wavelet responses that are going to approximate Gaussian derivatives. And in this way, the detector approximates the determinant of Hessian response. So that means the SURF is a blob detector. And in this case, the descriptor is a 64-dimensional vector that takes into account the sums of first-order hard wavelet responses over a 4x4 rectangular grid, which is rotate and scale according to a dominant orientation and scale. Vector-based descriptors or float-based descriptors such as SURF or SIFT, they perform quite well in several applications, but the main problem is that the matching of the descriptor can be computationally expensive because the descriptors have they are high-dimensional vectors, 128 dimensions in the case of SIFT and 64 in the case of SURF. So in the last few years, people have been trying to obtain descriptors that are easy to match and where the storage requirements are smaller or lower, especially in large-scale applications where you may have large databases of descriptors and you want to perform matching as fast as possible. One of the most popular binary descriptors is the binary robust independent elementary features, or BRIEF. And BRIEF is a binary descriptor that is based on pairwise intensity comparisons. And it has very nice properties, such as it has low storage requirements, is very fast to compute, and easy to match. Since it's a binary descriptor, we can use the Hamming distance, which is basically a distance that will measure the number of bits that are different in two binary strings. And this distance is extremely fast to compute in some architectures where we have some special machine instructions to count the number of bits set to 1 in a special register. However, the main problem is that BRIEF is not rotation or nor scale invariant. Now I will explain a bit how these pairwise comparisons work and how we can compute a BRIEF descriptor. So imagine, for example, that we have a patch centered around a key point, and this patch may have a size, can be 48 by 48, for example. So BRIEF is computed based on a set of pairwise intensity comparisons. So we have to define a set of binary tests, and a binary test is just simply the comparison between the intensity of two pixel positions in the patch, and we add the bit 1 if the intensity of the pixel I is larger than the intensity for the pixel j, and 0 otherwise. So in BRIEF we need to select the pairwise comparisons, and one of the approaches that gives better results in BRIEF is using a random Gaussian distribution to select the pixels from which we will compute our binary test, and we will obtain our descriptor. And the descriptor is just simply the concatenation of the output of n binary tests. So as we have seen, brief is very easy to compute, and we can get very nice performance in some applications. However, the problem is that it's not rotation and it's not a scale invariant. In order to try to overcome these problems regarding to rotation and scale, there are two methods that appear recently in 2011. One is ORB, which is oriented fast and rotated brief. And the idea is to be a scale invariant feature by using fast as corner detector, but fast is used in a Gaussian pyramid to get information about the scale. And also per key point, ORB is going to obtain a dominant orientation from which you can rotate the grid in brief and obtain a binary descriptor that is invariant to scale and orientation. However, in ORB, they show that by learning the set of pairwise comparisons for the binary test, you can get slightly better performance than when using a Gaussian distribution. A similar method is BRISC. It's a binary robust invariant scalable key points. BRISC is very similar to ORB since it's adding rotation and scale invariance to brief. However, there is an important difference with respect to ORB. This difference is that BRISC is using a predefined set of pairwise comparisons. For example, you can see the sampling pattern here in this figure. So the blue circles are the positions of the points in the patch from which we are going to obtain our binary descriptors, and we're going to perform pairwise binary comparisons with these points. And the red circles are, so in each point the intensity is weighted by a Gaussian kernel that has different standard deviation. So bigger circles, they will weight a bit more the intensity around that key point. There is the local difference binary descriptor, which was introduced in ISMAR 2012. LDB is based on the same ideas as brief, but it's adding another queue for the set of pairwise comparisons. So in this case, LDB is using intensity and gradient information to build a binary descriptor. And the way they do it is a bit different than in brief, since they compute intensity and gradient information averaging in a rectangular grid at different resolution. So you imagine that you have a rectangular patch. You are going to divide that patch in 4x4 rectangles, then 3x3 and 2x2. So in each of these resolutions, you are going to compute an average of your intensity and gradient, and you are going to perform the binary test considering intensity and gradient information between all the different subgrids that you have after all your subdivisions. LDB has the same problems as brief, since it's not designed to be rotation nor scale invariant. Now that we know about several feature detection and description methods, the next question to try to answer is how can we evaluate our detectors and our descriptors. So imagine that we came out with a great novel idea about a feature detector descriptor. So somehow we need tools to evaluate our detectors and descriptors to see if we are performing better than the state of the art or not. Thankfully, nowadays there are several benchmarks in the literature that they are really helpful for designing better and better detectors and descriptors. Possibly the most popular dataset is the Oxford benchmark. And this is a dataset for the evaluation of detectors and descriptors. So the dataset is composed of several sequences, and in each sequence you may have a different image transformation. You want to evaluate detectors and descriptors under different transformations, and this can be viewpoint, blurring, compression, zoom, changes in the scale, or illumination. Each sequence in the dataset is normally composed of 6 images, and the image transformation becomes a bit more complicated as long as we move from the first image to the last image in our sequence. And we have ground truth planar homographies between the first image and the rest of the images in each of the sequences. Another interesting data set, but in this case for image descriptors, is the learning local image descriptors introduced by Brown and colleagues in 2011. The nice thing about this data set is that it's composed of a set of corresponding patches, and these patches, they are all sampled from real 3D reconstructions of the Statue of Liberty, Notre Dame, and Half Dome. So this data set is, the patches are a bit more challenging because the patches are already capturing 3D information from 3D reconstructions. So this figure shows some example of the patches from the Statue of the Liberty dataset. Another dataset that I really like is the interesting interest points that it was introduced by Anais and colleagues in 2012. And this dataset provides very accurate ground truth because it was captured with a robotic arm, and they were also using an structured light scanner, so the evaluation already provides a 3D scanner for each of the images in the dataset. And also you have many different viewpoints and many different lighting conditions. So this is the ideal dataset in case you want to evaluate a feature detector or descriptor that you want to be invariant against different lighting conditions. Recently, Hanley and colleagues introduced in 2012 a comparative evaluation of binary features, and the idea of this work is was to create an extended evaluation framework from the Oxford benchmark, but focus more on evaluating the recent binary descriptors such as brief, brisk, orb, and freak, compared to the traditional vector-based descriptors that can be sift and surf. So this is an interesting data set for evaluating binary descriptors, and it also evaluates which of the different detectors descriptors combination works better, and in which kind of applications you may have better performance with a certain combination. Now let's talk a bit about descriptor matching. First, let's remember what is a descriptor. And a descriptor is basically a vector of data, and this vector of data contains local appearance information of a key point, of the neighborhood of the key point. And we have to differentiate between vector-based descriptors such as sift or surf, and in this case each element in our descriptor is going to be represented by a float or a double, and binary-based descriptors such as brief, LDB, brisk, and orb, and in this case each element in the descriptor is a bit, is represented by a bit. So in this case the descriptor is simply a binary string. For descriptors matching, we first need to define a distance or metric between them. And if we use vector-based descriptors, we may want to use the Euclidean or L2 distance, and in the case we are using binary-based descriptors, we will use the Hamming distance, because this distance counts the number of bits that are different in two binary strings. Then imagine that we want to match two images, and of course we want to match corresponding points between the images. So we will detect our features, compute descriptors, and compute the distance between all our descriptors. And we need to somehow to find a matching strategy to try to say that that pair of descriptors may be a good correspondence. And for that, we may want to use similarity distance criteria, which is basically if the distance between two descriptors is smaller than a threshold, you say that that's a correspondence, because since the distance between the descriptors is small, these descriptors may come from the same point. And another popular strategy is using the nearest neighbor distance ratio, which was proposed in the SIFT paper by David Love. And this matching strategy computes the ratio between the two closest neighbors of a given descriptor. So if this ratio is below a certain threshold, you will say that that will be a valid correspondence. And then imagine that we may have, in some applications, we may have millions of images and maybe billions of descriptors. So if we want to match the descriptors from one image to the rest of the images in our database, we need to come out with a good strategy. The first one that we may think is using a brute force approach, but this of course can be really slow in some large scale applications. So I do not recommend to use a brute force approach if your application has millions of images. And another strategy is using approximated nearest neighbors algorithms. In this case, we may lose several potentially good correspondences, but our approach will be much faster, and we will normally get very good results. And for this kind of approximated nearest neighbors algorithms, I really recommend to use the Flan library because it's a very good library for these problems. Now I will mention some of the criteria that people use to evaluate detectors and descriptors and to say that one is better than the other. So for detectors, normally people use repeatability, that this quantifies how repeatable a detector is. So this is, for example, we have a set of images of the same object, and we have different viewpoints. So we want the key points in all the images to be approximately at the same location in the scene. Then we have recall. That recall quantifies how many of the possible correct matches were actually found from the set of correspondences. Then precision is the number of correct matches out of the set of putative matches, and it's also known as the inlier ratio. So here we need to, in recall and precision, we need to differentiate a bit between the number of correspondences and number of matches. Number of correspondences is defined by your feature detector, given ground truth data, for example. So you detect points in one image, you detect points in the second image, you have your ground truth, and you want to identify with the ground truth how many correspondences you have between the two images. Whereas the number of matches is defined by your descriptor. So you will compute descriptors in one image, then compute descriptors in the second image, match the descriptors, and so you will have a set of putative matches. And then from this set of putative matches, you may have some matches that may be good, that can be the set of correct matches, and you will have some other matches that are going to be erroneous matches, and you normally identify the good matches and the erroneous ones thanks to the ground truth. And you also use some geometric validation criteria for identifying the correct matches and the bad matches. And this is normally you may use the pixel error location given ground truth and overlap area error. The overlap area error is used as a criteria to identify if two descriptors they are correct matches or not, or two key points are good or not. And the idea is it's very simple. So imagine that we have detected two points of interest in two different images. And these points of interest, they also have a region of interest that depends on the scale at which the points have been detected. So given ground truth homography, what we're going to do is project the key point from the image 2 and its area of interest into the image 1, and we are going to compute the overlap area error, which is basically the intersection between these two areas using the ground truth homography to project one region from one image into the another one, divided by the union. So normally if this overlap area error is below a threshold, this can be 0.5. So you may decide that these two key points are good correspondence, and otherwise you may say that these two key points are an erroneous correspondence. And there is this overlap area error, and this evaluation is available in the VL benchmarks. Then now they try to reproduce the Oxford benchmark, but they add some novel tools, and it's available in MATLAB, and it's very nice for evaluating in a very fast way your detectors and descriptors. So now we have seen several methods for feature detection and description and how to evaluate them. And I'm going to talk about one method I've been working in the last few years, which is called case features. And the main idea of this method is computing features from a nonlinear scale space. So we have seen that many approaches are based on the Gaussian scale space for detection and description. For example, we have seen that SIFT computes the Gaussian scale space, and SURF approximates the Gaussian derivatives using box filters. The problem of using the Gaussian scale space is that the Gaussian kernel, when we do Gaussian blurring or convolve one image with a Gaussian kernel, this does not respect the natural boundaries of objects and smoothes to the same degree details and noise at all the scale levels in your scale space. And the price to pay for this smoothing is a reduction in localization accuracy. So why not can we make blurring locally adaptive to the image data? So we will blur the noise, but we will keep some important details of our objects in the image. And the solution for this is using nonlinear diffusion filtering. So now we are going to show a video in which hopefully we will understand this better. So we have two figures here. The figure at the left just is going to show the evolution of that image through the Gaussian scale space. So we will see that as long as we go to coarser scale levels, everything is going to be very blurred. Details and noise will be blurred in the same degree. Whereas in the right image, we are going to see the evolution of an image through a nonlinear scale space. So what we are going to see is that when we are going to reach a coarse scale levels, important object boundaries of the objects are going to be preserved, and small details are going to be blurred. So now imagine here that we want to detect a feature and we want to compute a descriptor. So if we go to this window here in the Gaussian scale space, everything is blurred, so it may be a bit difficult to localize accurately a key point here and compute a discriminative descriptor because everything is very blurred, and this area of interest may look similar to this other window and this other window. But for example, if we go to the nonlinear scale space, we have preserved in the image important object details. So if we want to localize this window in this big scale, so this window probably is going to be, the localization is going to be better because we have preserved important object boundaries. And in the same way, if we compute a descriptor from this region of interest, the descriptor is going to be more discriminative because it's going to have more information about the local structure. So now we'll explain a bit what's nonlinear diffusion filtering and how we can get scale space representations as the previous one I showed in the video. So nonlinear diffusion filtering describes a mathematical framework that describes the evolution of the luminance of an image through increasing scale levels as the divergence of a flow function that controls the diffusion process. So L is going to be the luminance of the image, and T is the time or also the scale parameter. So it's going to be this evolution of the image through scale is going to be equals to the divergence of a certain function that depends on the pixel coordinates xy, and also depends on the scale, multiplied by the gradient of that image at that scale level. So the function c depends on the local differential structure, and is going to be, can be a scalar or a tensor. In case of features, we just consider this function to be a scalar function. So c is going to be a scalar value that is going to depend on the gradient, pixel coordinates, and scale information. And the time t is the scale parameter, as I said, and larger values will lead to simpler image representations. For choosing an appropriate function c, this function is going to depend on the gradient magnitude. And for example, what this function is going to measure is the gradient is important around a certain neighborhood. We want to preserve that gradient information into the scale space, so we will not perform diffusion at those locations. And we want to reduce diffusion at important edges location, encouraging smoothing within a region instead of smoothing across the boundaries of the object. So this function c is equals to a certain conductivity function that depends on the gradient. Perron and Malik in the seminal work of scale space and edge detection using an isotropic diffusion, they propose two different examples for this conductivity function. One is G1, and G1 promotes high contrast edges, and this is equals to exponential function minus the modulus of the gradient to the power of 2 divided by a contrast factor k to the power of 2 as well. And there is also G2 function that promotes wide regions over smaller ones, and this is equals to 1 divided by 1 plus the gradient to the power of 2 divided by the contrast parameter to the power of 2. So let's show some examples about this conductivity coefficient in the Perron and Malik as a function of the parameter k. So here in this figure, you can show the first row is the G1 conductivity function, and the second row is the G2 conductivity function for different values of the contrast factor k. You can notice that for increasing values of k, only the most important gradients or edges are preserved. So when k is small, we preserve most gradient information, but as long as we increase the value of the contrast factor, we just keep the most important edges in our image. So now let's show this video, in which this video just simply shows the conductivity function of Perron and Malik in a nonlinear scale space. So as long as we go to coarse scale levels, we will see that we will preserve most important edges. Okay, so the nonlinear diffusion filtering on the nonlinear diffusion equation, that's a continuous process. So if we want to perform nonlinear diffusion in our images, we need a mathematical framework to perform the discretization of this equation. The main problem is that there are no analytical solutions for the partial derivatives equations that are involved in the nonlinear diffusion filtering. And that means that we need to use numerical methods to approximate the differential equations. So the simplest discretization of the nonlinear diffusion equation is the explicit or forward Euler scheme, which is simply the difference between two scale levels of the luminance divided by tau, which is the time step, is equals to a certain matrix ALI that encodes the diffusivities of that image for that scale space, multiplied by the image at time I. So at the end, we come down to an iterative scheme that is shown in equation 10. The problem for this explicit scheme that each explicit iteration step is computationally very cheap, because it's just we just need to do some matrix multiplications and some additions, but we need to perform many iterations to reach a desired scale space evolution level. And the problem of this is because the discretization only converges if the time step is lower than 1 divided by 2 multiplied by m, which m is the dimension of our problem. In this case, m is equals to 2 for 2D images, but if you are performing nonlinear diffusion with 3D point cloud data, for example, m will be equal to 3. As I said, we need many iterations to reach a desired scale level, and this means that this explicit scheme, although it seems simple to compute, it's not going to be very efficient for feature detection and description, because normally we are interested in feature detection and description methods that are as fast as possible, so that can be used in real time. And definitely the explicit scheme, due to this convergence problem, is not the best way to go. But there are more efficient methods for nonlinear diffusion filtering. The group of Joachim Weicker has been working for the last, I would say, 20 years in developing efficient methods for nonlinear diffusion filtering. And now the two main methods that are completely stable for any time step are the additive operator splitting AOS scheme, and like 2 years ago they proposed a very nice mathematical method which is called fast explicit diffusion. So fast explicit diffusion computes dynamic time steps for performing nonlinear diffusion filtering, that the combination of them, they are at the end you have a stable nonlinear diffusion filtering. So this is the figure that they use with this rabbit here. For example, these time steps are very small, and this can be the explicit scheme. But what fast explicit diffusion is going to do, they are going to use dynamic step sizes. So one small one step that is going to be bigger, small, bigger, and so on. So you can reach much faster a desired scale level in your nonlinear diffusion filtering. And here you have some references if you want to go a bit more in detail about the nice mathematical details of nonlinear diffusion filtering, additive operator splitting, and fast explicit diffusion. Now let's talk a bit more about kase features. So kase is a Japanese word that means wind. And the analogy is, well, wind is defined as the flow of air on a large scale. And this flow of air is ruled by nonlinear processes. So we made the analogy with nonlinear diffusion filtering in the image domain. And also we decided to choose a Japanese word because in order to be in tribute to Taiso Ijima, which was the father of scale space analysis. So scale space analysis first time was discovered in Japan. And what kase is doing is performing feature detection and description completely in a nonlinear scale space. And this was first published in ECCB 2012. The idea in kase is going to be kind of similar as the idea in SIFT, and there are several steps. So the first one is given an input image, you are going to build the nonlinear scale space. So for building the nonlinear scale space, we are going to define a maximum evolution time for which we want to compute the nonlinear scale space. So you can see, for example, this image here. So we start with the original image at time 0, and then we perform nonlinear diffusion filtering up to a time tn, and at in this time tn we will have simpler image contents, but we have preserved main object boundaries, such as the main edges of this building here. So once we have computed nonlinear scale space, we are going to detect that features in that nonlinear scale space. We are going to compute the determinant of the Hessian response and perform non-maxima suppression in image and scale coordinates. So at the end, we are going to have a set of detected key points where the determinant of Hessian response is going to be maxima in a local neighborhood, in image coordinates and also scale coordinates. Then for each detected key point, we are going to compute a dominant orientation if that's desired. Otherwise, we can use the upright version of the descriptor, in which you do not have any dominant orientation, and that means that your descriptor is not going to be rotation invariant. But there are many applications where you may not need these rotation invariants because the camera basically doesn't rotate. Once we have set of key points and a set of orientations and an orientation per key point, we are going to build the descriptor. This descriptor is constructed according to a dominant orientation and the dominant scale, so the scale at which the key point has been detected. And the descriptor takes into account multi-scale derivatives, first order multi-scale derivatives in the horizontal and vertical coordinates obtained from the nonlinear scale space. So we are going to use a rectangular grid. This rectangular grid is exactly the same as proposed in the modified surf descriptor, but the main difference is that we are not using hard wavelet responses. Instead, we take into account the contributions of the derivatives from the nonlinear scale space. So this rectangular grid has an area of 24 by 24 pixels times the scale. So we divide it into different subgrids from which we take into account, we sum the contributions of the first order derivatives. So now let's show some of the experimental results that we can obtain with CASE in the Oxford benchmark. So first, let's start with the bikes dataset, where the chains are due to image blur. So this image here, it shows the detected key points in blue, and those ones that they are good matches, they are depicted with a red line between the two images. So the first figure at the left shows the repeatability score of the detector for all the images in the bikes dataset, and we compare the repeatability score of CASE against SURF, SIFT, and STAR, which STAR is a method in OpenCV which basically performs the same as the center surround extrema features proposed by Konolich and Agrawal some years ago. And basically it's a method that it's very similar to SURF, but they use a different set of box filters to compute the detector responses. We use different variants of CASE, so you can see here G1, G2, and G3. This means basically that we are using a different conductivity function for each experiment. So G1 and G2 are the two Perron and Malik conductivity functions that we have seen before, and G3 is another conductivity function that is described in the paper of CASE features. So we can observe that the repeatability score with respect to blurring is substantially better for all the variants of the CASE algorithm with respect to competitors. The second best performer is SURF, but the difference between CASE and SURF sometimes it's larger than 20% of repeatability. And the right figure shows recall versus 1- precision. So this measures the detector and descriptor performance. So again, we can observe that the different versions of CASE, they obtain much higher recall than the rest of competitors for any level of 1- precision. Now let's show some results for the both dataset, and this dataset the changes are due in zoom plus rotation. This dataset is a bit more complicated, so that's why we can see that the repeatability score of the detector decreases significantly as long as we move to the last image in the sequence. And for the descriptor, for the joint detector and descriptor performance, we can observe here that in this experiment, which is the image 1 versus the image 4, surf is performing a bit better, but the number of correspondences that have been detected and for which recall is computed, in the case of surf is 388, and in the case of CASE it's between close to 600 to 700. So that means that recall is a bit better for surf in this case, but they are using, the surf is detecting a lower number of correspondences compared to CASE. This is the Iguazu dataset. This is a dataset that was introduced in the CASE paper. This dataset tries to evaluate the performance of feature detection and description against changes in Gaussian noise. So nonlinear diffusion filtering normally was used in the past as a way of denoising an image that is corrupted with noise. So nonlinear diffusion is very good for these kind of denoising applications. So we can see here that, again, the repeatability score of the CASE detector is substantially better than competitors, and also we get a much higher improvement in terms of joint detector and descriptor performance in recall and precision. Here there is another example for the Leuven dataset. Here we have changes in lighting conditions of the images, and we obtain similar conclusions. The detector in CASE is better than competitors. Here this dataset is not very challenging, so the differences are not as big as compared to other datasets. And also the joint detector and descriptor performance is better for CASE than the other methods. This is the UBC dataset that measures the performance of features against changes in JPG compression. And again, we obtain better results for CASE in detection and also joint method performance here. And we evaluated also the performance of CASE features in image matching for deformable surfaces. And we were using a deformable surface detection method described in Pizarro and Bartoli in International Journal of Computer Vision in 2012. In deformable surface detection, so imagine that we have two images. We have the image of one template. The template is addressed, so that means the template or the object doesn't suffer any kind of deformation here. And then we have another image in which the template is deformed. So we want to find features in the template and match these features in the query image that has certain kind of deformation. So in these kind of problems, we cannot use classical epipolar geometry because the objects are not rigid. So we need to come out with different algorithms that are able to somehow to take into account this deformation of the surface. The method in Pizarro and Bartoli is based on local surface smoothness to discard outliers from a set of putative matches between the template and the deforming target image. In deformable surface detection, it's very important to have a high number of inliers in order to capture the deformation more accurately. So the idea is, as I said before, we detect features in the template image, and then in the target image, we match the descriptors using the nearest neighbor distance ratio to find a set of putative correspondences, and we use the method of Pizarro and Bartoli for computing the set of inliers and the set of outliers. So this figure here shows the number of detected inliers for this paper dataset, and we can observe here that the top performers are the different variants of CASE. So there are a significant difference in the number of inliers that each method is returning. So there is a difference at least 100 in layers with respect to star and surf, and a bit higher with respect to sift. So that means that Case features is also showing very good experimental results on image matching for deformable surfaces. We've seen before that we can obtain excellent performance in image matching applications using Case features. So the question that we were asking ourselves was, can we do it better and faster than Case features? And the answer for this question was yes, absolutely. And that's the reason why we released last year a novel method called accelerated Case features, or ACASE. I was working in this method with my colleagues Jesus Nuevo and Adrian Bartoli, so we published a paper called Fast Explicit Diffusion for Accelerated Features in Nonlinear Scale Spaces that was published last year in the British Matching Vision Conference in Bristol in the UK. So in this paper we show that we can obtain real-time features, compute from nonlinear scale spaces using highly efficient binary descriptors. And we introduced two main ideas with respect to the original Case pipeline. The first idea was to use fast explicit diffusion embedded in a pyramidal framework to dramatically speed up the nonlinear scale space computation. And the second idea was to introduce a novel modified local difference binary descriptor, or MLDB. This descriptor is inspired by the LDB descriptor that we have seen before, but MLDB is rotation and scale invariant, and also exploits the information of the intensity and gradient from the nonlinear scale space. So now we are going to watch a video in which we are going to watch an object tracking experiment where we compare ACASE with ORB and BRISC, showing that ACASE can obtain much better registration results and higher number of inliers in a challenging object tracking scenario. Now I will show some of the experimental results that we describe in the ACASE paper regarding detector, descriptor, and timing information. So the first image here shows the detector repeatability score in a synthetic rotation experiment, which the blue line here is the repeatability score of ACASE. So it's performing quite well. It's almost invariant to any rotation degree. The second top best port is the editor. Under method, they have lower performance compared to Case and ACASE. Here, this is the UBC dataset, which is JPEG compression, and we see again that ACASE is performing slightly better than Case, but it's like 7 times faster. So that's very good news. The other shows the repeatability score in the whole dataset against changes in viewpoint. So when the changes in viewpoint are more important, the repeatability score of almost all of the methods it's practically the same, and it's very low. So that means that there are still possible improvements for these feature detection methods in order to be invariant to affine transformations and changes in viewpoint. The figure here shows the precision of the ACASE method in the TRIS dataset for all the possible pairs of images in the sequence. And what we show is the performance with respect to the number of bits that is used in the descriptor. So one of the nice things in ACASE is that you can specify the descriptor dimension that you want to use. by using a random bit selection. So there may be some applications that you may get very good performance just by using 20 bits or 30 bits, and you don't need to store the whole descriptor. So for example, in this trees dataset, we can observe that in some of the image pairs, we almost get very good precision levels while using like a number of bits between 100 and 150. That means that there can be different applications where we may want to use different number of bits. This figure here shows the precision in the whole dataset, and I just want to show this figure so you can observe the benefit in the descriptor when you use the gradient information plus the intensity. We have seen that there are binary descriptors such as brief, orb, and brisk that they just use the intensity information for the set of pairwise comparisons in the binary descriptors, and LDB and MLDB, they also incorporate the gradient information. So for example here, this blue line is the precision for the images 1 versus 4 in the whole dataset just when using intensity in the Akase descriptor. Then if we add the horizontal and vertical gradients, we can get a gain in performance around the 20% in precision. That happens in the graphs here. These are the image 1 versus the image 3. We are using also gradient information. We're just using intensity only, about 20% improvement. This last figure at the bottom is the timing information in milliseconds for detecting 1000 features in one image of the graffiti dataset. This timing information doesn't take into account parallelization, because by means of parallelization, Akase can be computed in a faster way. So the main message here is that Akase is still very slow. It can be comparable to some SIRF implementations, but it can be slow for some real-time, some applications that may need real-time. So Akase is not the best way to go for real-time applications. And it's somewhere here, and it's slower than and Akase is fast. So somehow it's in the middle between very fast to compute features such as orb and brisk and surf. But the performance of Akase is much better than orb and brisk. So we hope that in the future we can speed up more the algorithm so we can have a faster algorithm and keep the same performance. The good news about Kase and Akase features is that this is an open source project, so the code is available under the BSD license. That means that you can freely take Kase or Akase code, use it for research purposes, or even use it for commercial applications, and you don't need to pay me anything. The code is based on a C++ implementation using OpenCV structures. Kase and Akase, both methods will be added into the OpenCV library. There are also MATLAB wrappers available, and now in the next future, I hope I will work on a GPU and mobile phone implementation that hopefully they will come out soon. So you can download the code either from my website or from the Kase website, or either by checking my GitHub account and download the code. And if you have any problems or questions while trying the code, please contact me, and I will be glad to help you to use Kase and Akase in your projects. Now I will talk about one application of interest that is using features, and it's visual odometry. Visual odometry, it can be either monocular or stereovisual odometry. Monocular visual odometry is a bit more challenging because you don't have direct information about the scale of the world. While in the case of a stereo, it's easier because by combining information from both cameras, you have information about the depth for a given point. So the goal in visual odometry is to compute the vehicle trajectory from stereovisual measurements. So what we have is a sequence of LED images and a sequence of images. Under time step, we have to perform a sparse feature matching between the left and right, so we can obtain a set of stereo correspondences, and to perform matching between a set of stereo correspondences at time 2 and a set of correspondences at time 1. So, by using this set of temporal correspondences, we are going to compute the motion between time steps with a translation matrix and a translation vector. Then we are going to accumulate the local motion estimate into a single global coordinate frame. So at the end, we can estimate trajectory of the camera in the scene. And we can build a dense 3D map of the environment. So imagine that we recover the incremental camera motion. So we can use that incremental camera motion in combination with dense stereo matching to dense 3D file these dense 3D reconstruction results. The left and right stereo matching is very simple. So we detect features in the left image and in the right image, compute descriptors and match the descriptor between the images by using the epipolar geometry. And once we have a set of stereo matches, we can triangulate the corresponding points and we can get the 3D information of each pixel. Then once we have a set of stereo correspondences at 2 different time steps, we can perform temporal matching. And in temporal matching, we want to match a set of putative correspondences between 2 different time steps. And then we want to find the best camera motion, and for that we are going to use a ransom-like approach. So we are going to propose a set of models from a set of minimum set of correspondences, and then we are going to find in an iterative process the best camera model, and then we are going to refine the best camera model with the set of falling layers. So at the end of this ransack process, we are going to have the incremental camera motion between these 2 time steps. In this video here, you can see at the left the temporal matching between 2 images at 2 different time steps, and also at the right you can see the accumulated camera motion of the trajectory in a global coordinate frame with respect to ground truth. Now here you can see the comparison of 2 different visual odometry algorithms with respect to ground truth. One of the problems in visual odometry is, like, since we are computing camera motion between consecutive frames, we are accumulating some drift over time. So that means that if we have a very large sequence, then at the end we are always going to have some drift in the trajectory with respect to the ground truth. In order to correct for this drift, we need to use loop closure detection algorithms and perform a post-graph optimization of the whole trajectory, for example. Now we can use the camera motion that we are incrementally computing for performing a dense 3D reconstruction of the scene. So I will briefly mention a dense 3D reconstruction pipeline that I was working last year with my colleagues Chris Beal and Frank Dellard, which is called Large-Scale Dense 3D Reconstruction from Stereo Imagery. So it has several steps. The first one is that you need to know the camera motion. Then the second step is to perform dense stereo matching between 2 stereo frames, and there are several dense stereo matching algorithms to get very nice disparity maps. And then once you have the camera motion and the dense disparity maps for a set of stereo frames, you can perform a multi-view geometric and photometric consistency analysis in order to reconstruct points between different views that will be added into the dense 3D reconstruction. And then finally, since we are dealing with millions of 3D points from a set of few stereo frames, we need to perform efficient light rejection and voxel grid filtering. So at the end of the process, what you can get is some results, as I'm going to show in this video. The first frames of the video, they just show the frames from the left image of the camera that is mounted in the vehicle that is acquiring the images. So at the same time that it's acquiring the images, we can perform incremental motion estimation and use that motion to build a dense 3D model of the scene. So at the end, in this case, the dense model is a dense 3D point cloud, but then from this dense 3D point cloud, you can build a mesh or triangulated surface or a nicer representation. But in this case, the model is basically a dense 3D point cloud of the scene. And you can observe that some structures of the environment, they are reconstructed with very high quality. So now let's move on to another application. Now I will talk about an interesting application in medical imaging that is using features, and this is dense 3D neoplasia modeling. What is dense 3D neoplasia modeling? Well, it's basically building dense 3D model of polyps in colonoscopy. And why do we want that? Well, basically because doctors and physicians, they use for classification on a standard technique called Paris classification that relies on 3D information of the polyp, such as, and they look at parameters such as size, shape, and depth of invasion into the submucosa. So if doctors, they can have and they can look at the dense 3D model of the polyp and they can perform measurements about the size and shape, this will facilitate the diagnosis. So when we look at this problem, we thought about using enhanced endoscopy modalities such as narrowband imaging or NBI, which is a novel endoscopy modality that plays a bit with the wavelength of the light from the endoscope and also the light absorption by the tissues in the body. And then chromoscopy, which chromoscopy is a technique, it's an invasive technique that introduces a contrast agent into the body. So in any case, enhanced endoscopy modalities, they facilitate the structure from motion because they improve the texture of the area of exploration. So we can understand this a bit better. So now we are seeing a video using a standard endoscopy, white light. So we can see that it's very difficult to run a structure from motion pipeline with this kind of texture because we have so many textureless areas. So it will be very difficult to detect features and find correspondences. But if we use narrowband imaging, NBI in this case, so we get a nicer texture that we may be able to reconstruct this in 3D model with a structure from motion. And then if we use chromoscopy, we have this blue nice texture that can be very good for a structure from motion. The dense 3D neoplasia modeling has several steps. So So the first step is to use a video stream of enhanced colonoscopy images. We are going to detect a set of features and compute descriptors and perform a rigid structure from motion. So this approach, we consider that the doctor is not deforming the polyps under the area of exploration, so everything is rigid. So we perform feature detection, description, and matching, and then we perform a sparse 3D reconstruction with optimized karma poses using bundle adjustment. Once we have a sparse 3D point cloud and a set of reconstructed camera poses, we perform identification of the 3D point cloud using multi-view stereo methods, such as, for example, Furukawa and Pons, patch-based multi-view stereo, or other techniques. And once we have a dense 3D point cloud, we construct a triangulated surface using Poisson surface reconstruction. And finally, we perform an scale estimation using a combination of depth from focus and depth from the focus techniques and calibration data. So at the end, we can get a dense 3D model of the area of exploration where the doctor can perform measurements and look at the size of the polyps, and etc. So this figure shows one example about the problems when we want to use a standard endoscopy versus enhanced colonoscopy. So for example, this is a figure of the same polyp in the area of interest, but figure at my left is using a standard endoscopy and the right is using chromoscopy. So the number of detected features in the first case with the same, in this case we were detecting surf features using the same detector threshold, is 138 compared to 1069 using chromoscopy. So the conclusion here is that when we use enhanced endoscopy, the texture is improved so much that we can reliably detect a higher number of features and then perform structure from motion more efficiently. And here there are some results of the dense 3D models that we got. So the first row, they are some images of some colonoscopy explorations, and then the second and third row, those are images from our dense 3D models where the doctor is drawing the perimeter of the polyp of interest and is measuring the diameter with that line in red. So, and we also show the length of the diameter of the polyp of interest. Now I will talk about the last application that is using features in this seminar, which is the formable 3D reconstruction with an object database. So the goal here is to perform the formable 3D reconstruction from a single image and for multiple objects simultaneously. So this is a work I did in the past with Adrian Bartoli, and we presented in the MBC conference in 2012. So the goal here is that we have an object database that is composed of a set of different objects, and for each object we store some geometric and some appearance information, and we have an input image. So we want to detect the object database, some objects from the database in that input image. So once that we have detected the objects and we have the registration between our input image and the objects in our database, we can perform the formable 3D reconstruction. The object database is, comprises of developable and non-developable objects. By developable objects, I mean those objects that are planar objects, such as, for example, these pieces of cloth here, or the amazing Spider-Man flag here, or this t-shirt, or this magazine. And for non-developable objects, these are the ones that are non-planar, such as, for example, this cushion here or this cushion here. So each object in the database is going to be composed of a set of appearance descriptors and a 3D template and a 2D parameterization of this 3D template. Depending if the object is developable or non-developable, we are going to use different techniques for building the 3D and 2D templates that we need to store in our database. For the case of non-developable objects, we are going to take a set of images of the object. So we are going to detect features, run an structure from motion pipeline with the scale information, so we can obtain a 3D point cloud here, from which we can build a 3D mesh, and finally we can obtain our 2D conformal parameterization. In this case of non-developable objects, we are going to use 2D conformal mapping, which is a very popular technique used in computer graphics to parameterize a 3D mesh into a 2D mesh, and this is widely used, for example, in texture rendering. For the case of developable objects, so we are going to use a single image. We are going to detect a set of features and descriptors, and since we know that the object is planar and we know the dimensions of the object, obtaining a 3D reconstruction of the object is very easy. And then from this 3D reconstruction, we are going to obtain a 3D mesh, and since we know that all the 3D points in this 3D reconstruction, they lie on a 2D plane, so we already have our 2D parameterization of the object using the plane information. Once we have the database of objects, the deformable 3D reconstruction pipeline works as follows. First, we run an object recognition approach, just using a hierarchical vocabulary tree to find a set of potential object candidates present in the image. Then for each of the potential object candidates, we perform feature-based deformable surface detection using a weight baseline matching approach with outlier rejection based on local surface smoothness. This is the approach I described when I was showing the experimental results of CASE features for deformable surface image matching problems. As the image deformation model, we are going to use the thin plate spline warp between the selected templates and the target objects in order to capture the deformation properly. So once we have a set of potential object candidates from which we were able to compute a thin plate spline warp that captures the deformation, we are going to obtain the deformable 3D reconstruction of the object. And we do this under the assumption that the surface is deformed isometrically. So under this assumption, we can obtain closed form solutions for the 3D surface depending only on the image warp and the set of first and second order warp derivatives and non-camera intrinsics. In these figures, we can observe some of the results of applying the outlier rejection algorithm in deformable surfaces. So the first row is for non-developable objects. So first, this is the set of correspondences between our input image and our template of the object in the database. So we can observe that there are many erroneous correspondences, but then after running the outlier rejection algorithm, we have a set of cleanup matches from which we can reliably compute thin plate spline warp to capture the deformation properly. And the second example at the bottom is for a developable object. And here is the same. So this is the first set of correspondences. So we may have some erroneous correspondences. And after running the outlier rejection algorithm, we come out with a set of good matches from which we can estimate our thin plate spline warp and capture the deformation properly. Let's see now some of the experimental results. In this example, we are considering one single object in the image. So the user is waving a t-shirt, and the system is going to detect the t-shirt from the object database in the input image, and it's going to perform the registration between the input image and the template in the database. And once we have the registration, the system is going to estimate the deformable 3D surface of the object. So now in this video here, we can observe how the system is performing the registration between the template and the input video, and then at the right we can observe the estimated deformable 3D surface of the object. In this example, we can observe several figures considering two objects in the image. So the first row shows the registration between the objects in the image and the templates in the object database, and then the bottom row that shows the estimated 3D surface of each of the objects in the image. So now I will show some conclusions about this seminar and also provide some future directions about this area of research in computer vision. So in this seminar we have reviewed the main methods for 2D feature detection and description. You are very welcome to use CASE and ACASE in your research projects or even commercial applications. They are very nice methods, they provide good performance, and they are completely free, so there is no patent restrictions for using these methods. We have also covered some applications of interest, but there are many more applications. And some future directions is we should come out with novel feature detection and description methods that are more robust against some difficult image transformations, such illumination changes due to changes between day and night or through seasons. Also some difficult transformations due to viewpoint and deformable surfaces. So we need better features for this kind of difficult transformations. And also the extension of some of the feature detection and description methods from the 2D domain to the 3D domain. So in the next future, 3D is going to be everywhere. So our tablets and our mobile phones, they are going to have depth cameras. So we need to come out with very efficient methods for feature detection and description in 3D data. So if you have any questions, please contact me. You can check my website, this written there. And you can send me an email if you have any question or suggestion. So thank you very much for your attention.